permit. Yeah, it starts. So welcome everyone. This is Michael Young from Netherlands, University of Twente. Welcome again to this fourth session. So now we have Raf Batra, associate professor from Georgia Tech, and also associated with Facebook at the moment. Yeah, Facebook AI Research Fair. Okay. So a very brief introduction of him. He was assistant professor and briefly in before that in Georgia, in Virginia Tech. Sorry, from 2013, 2016, and before that he was a research assistant professor at TTIC in Chicago, and he did his PhD in 2010 from CMU. And about his research and his interest in general AI, and also lies in the intersection of machine learning and computer vision, with part into the NLP. Okay, so I think he's, for me, he's most well known on this diverse solutions, MIF, and also the VQA recent works. So I'm looking forward to your talk, Raf. So
thank you, Michael.
The floor is yours.
Yeah. Thank you, Michael, and thank you to all the organizers for having me and for organizing this workshop. Before I begin, I just want to acknowledge that in the US today is Juneteenth. As was mentioned, I'm affiliated with Facebook AI Research, and I've spent all of today at an internal event on discussing the history of the event in the US and the continued systematic implications on the African American community, particularly in the US. So I just want to acknowledge that this is a important event in the US today and with implications globally. But I hope we're all taking the time to learn about it and educate ourselves. Okay. So as was mentioned, I'm a faculty member at Georgia Tech, and I'm also a research scientist at FAIR. Today, what I want to talk to you about is this line of work that we've been pursuing on disembodied to embodied multimodal learning. And let's start diving into the pieces here. From my perspective, I think there's almost like a paradigm shift happening across a range of communities: computer vision, NLP, robotics, machine learning, from in the transition from disembodied AI, which you would think of as learning from static data sets typically collected from the web. These could be images or text, to more embodied settings, which involve agents acting in environments. These could be physical agents like robots taking actions in the world, talking to humans in natural language. So things like, a human talking to a robot in a dangerous situation, like, is there any room, is smoke in any room around you? With the robot perceiving, replying yes in one room, and following instructions like go there and look for people. Or embodied AI could refer to virtual agents. These could be egocentric, smart AI assistants. So virtual agents on smart glasses taking virtual actions, talking to humans again in natural language. In this case, the embodiment or the body is not of the agent, the body is of the human wearer, but a lot of the same challenges apply. There's egocentric perception. You can have scenarios like, where did I leave my keys? And so the agent can answer things like, on your coffee table. Okay, if there's a augmented reality display, show me the recipe for making guacamole, and so on. And so the common theme here is that there is embodiment. There are agents, there's active perception, and there's learning from a different paradigm. And as soon as we do that, we have to deal with some problems that people in computer vision may not typically have dealt with. So egocentric data, and this is a video from Kristen Grauman's group, it looks very different compared to the nicely curated data sets that we often work in the disembodied data set settings. But this is both an opportunity and a problem in the sense that this is now an active perception problem. The agent, controls the distribution of information coming its way. Your actions have consequences, and so you can do image stabilization, or you can just stabilize your body, and so some of the jerkiness will go away. But what you see is a consequence of your actions. The other main sort of problem, and this is where the machine learning community comes in how they think about this problem, is that in the disembodied setting, what tends to happen is a lot of supervised learning paradigm. We make a prediction on a particular instance, it's an image, or it's a sentence, or it's a speech signal, and we get fairly dense supervision. Here's the right answer if you're doing image classification, and here are all the wrong answers. In a lot of tasks that we're going to be talking about, it's a long sequence of actions, and at the end you get a reward about whether you succeed or not. And this is, of course, this reinforcement learning paradigm, but that's not the only paradigm that deals with this problem. The idea that you have to make a long sequence of decisions, and then you get often sparse reward or supervision. And finally, like a topic that is close to a lot of to my heart, but also broadly studied, is grounded language understanding. Instructions have to be grounded in the perception, and that this is not a disembodied English to French translation where there is no meaning of the words. You have to, to follow instructions like, is there smoke in any room around you? You have to look around you, and smoke has to mean something, and room has to mean something. And in order to execute those instructions. And finally, in the motivation section, I'll say, if none of this convinces you, there was a workshop at CVPR, at this CVPR, on Sunday and Monday this week, at the beginning of the conference, that we put together a broad group of coalition of researchers across 15 different institutions put together, which is called the Embodied AI Workshop on this topic, where we were fairly lucky to have eminent scientists in cognitive and development psychology, Alison Gopnik and Linda Smith, talk about motivation for embodied AI research from human and child learning perspective. And so if you're, if my arguments don't convince you, I would refer you to check out these talks that are recorded and available at this workshop. It's extremely high quality content where you get to hear about what humans are capable of, how babies learn from an embodied setting, and how there might be ideas in there for the way we approach AI problems. Okay, what I'm going to do today is talk about 3 specific projects. They are going to be in the direction of moving from disembodied multimodal learning, vision and language type multimodal learning, to embodied setting. These are 3 different projects. So let's start with the first one. This is work led by Arjun Majumdar, who's a PhD student at Georgia Tech, in collaboration with just a fantastic group of collaborators. Ayush, who's a master's student, Stephen Lee, who was a research scientist at Georgia Tech and is now a faculty member at Oregon State, Peter Anderson, who also was at Georgia Tech and now is at Google, and Debbie Parikh. The problem we're trying to solve in this is instruction-guided visual navigation, or what is also known as vision and language navigation. It consists of an agent, a virtual robot, if you will, that is at a particular location in an indoor environment, and is given instructions like, take a left, go down the hallway, turn into the bedroom, on the left, stop at the foot of the bed. And it has to execute a sequence of actions to go from where it is to a particular goal position. The agent has to do this, obviously, from egocentric perception. The agent does not have a map of the environment. This is purely for visualization. And this is what that may look like. So this is a slightly longer instruction that says, walk through the bedroom, out of the door, into the hallway, walk down the hallway, along the banister rail, through the open door, continue into the bedroom with a round mirror on the wall, and butterfly sculpture. So there's a fairly long instruction. You see the agent sort of take a sequence of actions, turn right, turn left, move forward. This is a panoramic image. That is why you're seeing distortions straight lines looking curved, and then ultimately the agent calls stop at, and you can see that there's a round mirror on the wall. There's like this butterfly sculpture that we can see. This is a top-down map on the left. I hope people can see my my cursor. Let's see. So hopefully this is visible. That there's a top-down map with a grid shown. So this is the problem that we're studying. We are given instructions: walk through the bedroom, out of the door into the hallway. There is a navigation graph. So on the floor plan, there are certain locations. There is an irregular graph that has been pre-constructed in this environment. And we are not doing continuous navigation, but hold on to this thought. I will come back to it in the second half of this talk. And that this node is where a panorama was taken. So this node corresponds to an observation at this node corresponds to this panoramic 360-degree image. These are the observations. You can turn around and that just rotates the panorama, or you can move along the edges on this graph. And that's the navigation that you have to construct. The difficulty here is, of course, is grounding the words that are referred. So there are some words that are, walk down the hallway. That's a fairly simple instruction, but there are every so often words that are fairly specific and unique. Banister rail. You have to understand what a banister rail is if you want to walk down the hallway along the banister rail. You have to continue the bedroom with a round mirror on the wall. Here's the round mirror, and that there's a butterfly sculpture. That butterfly sculpture is shown on the right in the green. So there are things or tokens or words in the instruction with corresponding visual observations, but nobody gives you this correspondence. You must discover it on your own. And of course, this is just a special case of a more general problem. This is called the simple grounding problem. This is a rich history in natural language processing and AI, broadly speaking, about how do we go from symbolic representations to sensory motor perceptions. How do we connect those two so that intelligent systems can take actions in the real world, as opposed to being purely symbol manipulation systems. And this is not just a scientific problem. This is also an engineering concern. Statistically, the data distribution, so if you look at the occurrence of various words in the instructions, they follow, as you might expect in a lot of these data sets, sort of a fairly long tail distribution. But more importantly, there are some words that are seen quite frequently: room, stairs, door, right, left. They're extremely common in these instructions. But things continue out for a long time, and there are lots of words that appear just once. You see this word mentioned once in the instruction. Maybe you see it at training time, maybe you see it at test time. At test time, if that happens, then it's a completely new word, right? You've never seen this before. And so things like there's a scarf, only mentioned once. It's a frequent enough word in reality, but when people are describing navigation, maybe they don't mention scarves. Love seat, marshmallows. And so anytime this word happens and you're told to stop at a love seat, if you don't know what it looks like, this instruction will fail. We'll be unable to solve this problem. And so the approach that we take in this is to step back and ask ourselves, we've been here before. The vision and language community, grounding tokens into perception is not new for that community. And so the approach we're going to take is to transfer visual grounding learned from large-scale internet data, so the disembodied supervised learning dataset setting, to this embodied setting. The dataset that we're going to use is this fantastic resource called Conceptual Captions dataset, which is a dataset of images from the web and modified alt text from those images. So, for this image, pop artist performs at a festival in a city, a worker helps to clear debris, blue sofa in the living room. They are noisy because they're automatically curated and created, but they are extremely large in scale. So we're looking at 3.3 million pairs of image text pairs. And the question we're asking is, can we leverage this data to perform vision and language navigation in new environments where we don't have a lot of data of this kind? The key problem we'll have to solve is, of course, the internet to embodied transfer learning problem. Internet or web scale data tends to look very clean. It's a well choreographed, well captured moment in time where when we talk about blue sofas in the living room, you're seeing it from head on. Maybe the object is in full view, it's well lit and so on. When we are doing navigation in these panoramas and you're trying to go in a particular direction, the sofa that is mentioned, you might view it from a weird angle. It may be thin and off to the side. It may not be fully visible. And it may be visually fairly different from what you have seen in the data set. So this is the transfer learning problem that we've set out to solve. And so here are more examples of what these things look like. So this is images of various categories from the conceptual captions dataset and from Matterport 3D scans. And so, couches, so you don't even notice that there's a couch here, but right here on the left here, it's just incidentally off to the side because that's not the point of this image. Doors, when you find them in web images, are typically closed. When you find them in indoor navigation type images, they're typically open, because if the door was closed, you wouldn't be able to go through it because we haven't built the technology to have robots that are opening doors. So typically these are open doors. That's why navigation is happening. And the lighting of these things might be different, and the clutter might be different, and so on. And the perspective view, of course, is different. So this is the transfer learning problem that we set out to solve. And the way we're going to do it is we're going to go in terms of model classes. There is a model called Wilbert that we had published at NeurIPS last year with these set of collaborators, Jason Liu, who was a PhD student at Georgia Tech and is now a research scientist at AI2. And he led this work. And we're going to adapt this for vision and language tasks. So the key Wilbert is a multimodal transformer model for vision and language tasks in general. But the key insight in Wilbert is to construct a joint transformer that has a vision branch to it and a language branch to it, or the image branch and the language branch is a sentence. This is trained on data sets of such paired data, and that's coming from conceptual captions again. The way we are, and the innovation or the technical novelty here in this model is the fact that the vision branch has sparse cross-modality attention into the language branch and vice versa, which allows or encourages grounding of tokens into regions. And that's the one thing I should mention, that the image is first converted into regions from a FastRCNN model trained in visual genome, and those regions are fed as visual tokens into this transformer model, so that when you are attending from one token here to another token here, grounding develops through unaligned or unannotated, but we don't have word level alignment in this paired data. The way we're going to train these is through standard masked prediction or self-supervised learning paradigms, in that we're going to take some visual tokens which correspond to regions, we're going to mask them. We're going to take some language tokens, we're going to mask them. And for the masked tokens, we're going to predict either the visual representations or the language tokens that were masked. And everything else is visible. So you get to see all other parts of the image, and you get to see some words, and you have to predict the visual representation of the region, in this case that corresponded to a man, and these words. And so this is what might encourage grounding. No additional supervision is needed for this stage. And ultimately, for any particular task like image caption re-ranking, you can fine-tune these representations by having an alignment sort of a metric score that does this. Now, that was a quick recap of Wilbert. What we're going to do is, that was designed for web scale images, conceptual captions, with results demonstrated on VQA, image caption re-ranking, and a number of other sort of disembodied setting tasks. We're going to transfer that over to vision and language. And quite deliberately, we're going to try and make fairly minimal changes to this architecture. And the reason why we're making minimal changes is because we want to reuse as much of the weights and the pre-training as possible. We have set out on a task where we do not have a lot of data. So major cuts or modifications to this architecture will result in loss of ability to reuse those parameters. And so this is a fairly deliberate choice. And what we're going to do is, first of all, our images are coming from these panoramas. So now we have a sequence of panoramas. We don't have a single image. We have multiple panoramas. And we have a sequence of instructions, which are still concatenated. So there are words. I encourage you to read the paper, but there's a fairly well-defined procedure for taking a sequence of panoramas and converting them into a sequence of regions with specific embeddings mentioning what part of the image and which panorama they came from. And so the regions now correspond to various panoramas and the words correspond to the instructions. And the thing that we're going to do differently is we're going to treat this as predicting compatibility between an instruction and a particular path. And so where do these paths come from? We're going to actually be in the setting where we have done some pre-exploration in this environment. So we're running, we're going to use this model just to re-rank a sequence of trajectories in this environment. And so this is a particular shortcoming of this approach, that this only works if this is only a re-ranking mechanism of trajectories. And we're going to investigate and remove that shortcoming in future work. But for now, just think of it as measuring compatibility between a sequence, between a trajectory in the environment and an instruction. And we can measure compatibility based on how whether the path was successful in reaching the right place. Okay, the key sort of benefit, and this is where all the benefits kick in, of making minimal changes from Wilbert is that we're going to be able to reuse a lot of the training. There's 3-stage pre-training curriculum to this approach. The first stage is that we're just going to do language-only pre-training, just like in BERT and in Wilbert. So you just see, there is no visual branch, you just see the language branch, a couch, also known as sofa, blah, blah, blah. And this is coming from Wikipedia text and so on. Then there's going to be the image caption pair training on conceptual captions. So an image and a caption, the image from web data, and we're learning alignment and re-ranking of this task. And finally, we're going to fine tune for the sequence of panoramas and instruction matching for the vision language navigation task. And because we've made minimal edits to the architecture, this first stage, the language branch, can be initialized from BERT, and the second branch can be initialized from Wilbert, and then the fine tuning can be done on the small amount of data, relatively speaking, compared to these other tasks that we have on the VLN R2R dataset, room-to-room navigation dataset. And what we've done is a fairly thorough set of experiments showing that this is valuable. All of these stages are valuable. So if you don't do any pre-training, if you just take our architecture, VLN BERT, and train only on the room-to-room data set on the vision and language navigation task, you get roughly 30% success rate. Success rate is whether you got to within a distance threshold of the place, of the position on the graph that you were trying to get to. 30%, then these are, about roughly 1/3 of the time you're able to get there. If you do just the language pre-training, so no conceptual captions, just on Wikipedia data, you're doing pre-training of the language branch and then fine-tuning on R2R, already there is a significant improvement of 15% in success rate. If you're doing language and visual grounding, so pre-training on conceptual captions, and then pre-training on BERT, and then on conceptual captions, this is significantly increased. If you're directly jumping from language to R2R dataset, then we're somewhere here. And the full curriculum, we're at 59%. So there is an improvement of 9% even from the closest method, but with no pre-training, there is a significant jump. So from 30 to nearly twice that performance in success because of these stages of pre-training. So we are really benefiting from the amount of data. It's not just the architecture doing the heavy lifting, it is the pre-training, and this is the benefit of doing minimal edits to the architecture. And this is the leaderboard of vision and language navigation on Eval AI, which is an evaluation platform. till about a month ago or a few months ago, we were the top entry. Right now, this is the second entry because the top is humans, of course. It's slightly behind. I wouldn't read too much into the significance of these things. I do want to highlight that we're, as a community, this is a highly competitive data set and a highly competitive leaderboard. There's lots of methods and entries on this task. And as a community, it appears that we are beginning to make progress on this task. I mean, after all, if you look at this, success rates are beginning to get into like 73, 74%. The SPLs, which is a measure of efficiency of the path, are low because this is the pre-explore setting. So all, a number of trajectories are being re-ranked, but 73, 74% is pretty high of the episodes that you appear to follow these navigation instructions. And I'll come back to this number in the next bit. I think we are not here yet. I would claim that these numbers are actually inflated. And as a community, we should revisit this, and I'll talk about this again. Okay. I think some of the qualitative results here we were pretty excited about. We found that in a lot of these cases, here's an example: turn right, then turn left, turn right into the room, then wait near the antelope head. In order to wait near the antelope head, you have to know what antelope head looks like. This is a pretty rare word. And what we can do is we can find, for example, the regions with the highest attention corresponding to this word. And that, in this case, is this region, which gives us some confidence that this grounding is actually emerging, that at this particular point, it corresponds to this panorama taken from this location, which is the last place where the agent stops. The agent does not follow the path exactly. It follows a slightly different path, but it stops at the right place, and then it appears to be looking in terms of the attention with the highest weight at the right region, which is quite promising. Here's a illustrative failure case we found. Walk out of the bathroom, pass the sink in the shower, walk down the hallway through the arched entry and circular tile room, turn and walk into the bedroom, and hanging curtains, wooden bed frame. The agent actually fails. It ends, the ground truth path goes here, the selected path, agent path, goes here. This is a failed trajectory, but actually when you look deeper into it, the region with the highest attention corresponding to this is at a different point in the trajectory. It actually does look at a curtain. It just is not looking at the curtain corresponding towards the end. So this actually is highlighting a deficiency in our approach, that there is nothing forcing the attention to be aligned in a way that near the end you should look at trajectories that are near the end and so on. So there are definitely room for improvement in this model. But the sort of pieces and the low-level ideas are there. You need to know what tokens correspond to, and that needs to emerge. And you are never going to have enough data in this scenario, so you have to learn it from somewhere else. And you can ask whether visual groundings are actually improved by pre-training, or is this just a property of the model architecture? And we actually looked into that question, and the answer is resoundingly yes. Pre-training does help visual grounding. And here's the more details are in the paper, but here's a qualitative example illustrating that. Go through the door to the right of the door of the wine room, go straight to the right of the table, turn right, and go into the door next to the mini fridge. If you pre-train Wheel and BERT with conceptual captions, it will find a region where it is looking at a mini fridge. If you take the exact same architecture but do not pre-train with conceptual captions, not only will the trajectory fail, but the region with the highest attention will not be the one which is mini fridge. So this right here is a fairly controlled case. Right? This is telling us that when we do pre-training on conceptual captions, it actually directly helps in grounding of the tokens that are mentioned in the instructions, which is exactly what we set out to. So that's nice to know. Okay, so that was a project called Wheel and BERT, where we're borrowing data, disembodied web data for multimodal tasks in an embodied setting. I will now talk about the same task, vision and language navigation, but in continuous environments. This is with a set of collaborators at Oregon State, led by Jacob Krantz, who's a PhD student of Stefan Lee at Oregon State, also in collaboration with Eric Weinitz and Arjun Majumdar, who are PhD students at Georgia Tech. And I think our starting point of this was, asking, why is it that we are doing navigation on this navigation graph? Vision and language navigation, I said you have to follow instructions, and I said, there's some pre-computed graph on which we're doing navigation. But it's worth asking, well, why is there a graph in the first place? Where did these nodes come from? Why aren't they located at any other location? How is this edge defined? And why are we committed to a graph in the first place? And the reason why the agent is committed to navigation on this graph is because all of this research is being done on a data set called the Matterport 3D dataset, which was released a couple of years ago. And Matterport dataset was collected released from this company called Matterport. This is a 3D scanner that Matterport makes. This is a lab at Georgia Tech with my student Joanne Truong. And this is a physical 3D scanner. Put it on a tripod, and you place it at various locations. So these circles on the floor are the locations where this was placed. It actually spins around, takes a 360-degree panoramic image, and that is where navigation is happening. It was a choice made by whoever collected this data set when it was scanned in these indoor environments. That's all nice and all. But it can actually lead to a number of problems when you want to study this particular thing, this particular problem. And some of the problems here are that by working on a navigation grid, we already assumed that the topology of a new space is known. So it's a new house. I'm supposed to navigate in an unseen environment, but somehow I know the topology. I already know where all the nodes are and which nodes connect to which node. And that's an unrealistic assumption out of the bat. If it's a new space, it's a new space. You couldn't have constructed a graph in that new space. The second problem is there is oracle navigation. By saying that move forward, you know where you're going to end up. Real robots do not always know where they're going to end up. There is actuation noise. When you decide to move forward, you cannot be 100% certain that you will always land up exactly at the waypoint that you set up. So that's one thing that we already assumed. And we didn't even realize that it was assumed. It was just implicit. It was hidden away into the navigation graph. And finally, the third thing, we just assumed perfect localization. By knowing that you are at this node I, j, or at node I in this graph, and knowing that your neighbor is j, you know where you are. There is perfect localization. There is never any noise. And I implore you to talk to your robotics colleagues, and they will laugh at this assumption that localization is perfectly solved and you always know where you are. Real robots do not have perfect localization. It needs to be computed on board. It has noise. In indoor environments, GPS does not work very well. And this is just, given the technology at hand, this is an absurd assumption. So these three assumptions were being made just by assuming a nav graph framing of the problem. And what we basically said in this paper is that these assumptions are not realistic. And if we have to make progress as a community towards real navigation and be able to be taken seriously by anyone who's familiar with navigation, these assumptions have to go. And so you have to lift yourself from a known topology to a full 3D simulation. You have to go from Oracle waypoint-based navigation to some low-level actions like move forward, turn right, turn left, move forward maybe 0.2 meters, turn right 10 degrees, whatever. The exact values don't matter, but it has to be some lower-level state navigate actions than being able to go precisely to a waypoint. And you have to not know where you are, or you have to derive it from noisy sensors. You cannot have perfect localization. And so what Jacob and others have done is lifted vision and language navigation from this nav graph setting to full continuous 3D environments. So on the left, I'm showing you an episode of following this instructions: leave the bedroom, enter the kitchen, walk forward, take a left at the couch, stop in front of the window. The green dots here indicate the placements of the Matterport camera, and so that's the navigation graph. That's what an agent would do in the previous version of the problem, and the blue is continuous navigation, and that's what we're visualizing here. This is done in a simulation environment called Habitat, which is a project that I lead at Fitzpatrick AI Research with a number of multi-institution collaborators. And the way this is done is that Matterport camera that I showed does not actually just produce panoramas at those locations, but you can actually get full 3D reconstructions. So this is Joanne, again, placing the Matterport camera at various locations. And this is the full 3D reconstruction of this indoor environment captured, again, from Matterport. And then it can be loaded up into a simulator to simulate navigation from arbitrary viewpoints. There are some technical challenges here that you almost immediately run into. Is that this seems like a simple thing. Okay, we had a grid graph or an irregular graph on a floor. We have to convert it to 3D reconstructions. How hard could it be? Turns out anybody who's worked with 3D reconstruction understands that it is not a solved problem. It is not perfect. Often there are holes or missing geometry. So sometimes if there is a reflective surface, it will result in a hole in the mesh. And so that point, that node may not actually project to any valid location on the mesh. Or it may be that it projects to something where it is occupied by another object. And typically this happens if the tripod was placed close to or right over another object, and so you're trying to project it onto the floor, or maybe there are reconstruction errors, and now you have a collision. A robot cannot actually climb onto this location on top of another object. And so in these cases, we find the nearest navigable point on the floor mesh in these cases. I refer you to the paper for details. And I encourage you to actually look at this data. There are in a number of cases problems with geometry and textures. So this is a difficult problem. It is an active research area. But the interesting things about vision and language in continuous environments is that the action sequences are long. This is the turn right, turn left, go forward, 3 possible actions. The average number of actions in the shortest paths from start to target is somewhere close to 55. And you compare that to most navigation in vision and language navigation is 5 to 7 hops. At that point, 5 to 7 hops in a graph is not really navigation. It is graph search in a fairly shallow graph. And this is real navigation where you have to take a sequence of actions in this environment. You can sometimes have as many over 100 sequences. And when you have 100 sequences, you cannot do full pre-exploration of the environment. You actually have to act on the fly. So if we've done this porting over, you can ask a question. So how well do popular vision and language methods transfer over to the setting? And the short answer is poorly, extremely poorly. We've taken a number of standard family of methods, standard sequence to sequence type methods where you take RGB and depth perception encoded through a ResNet. You take your language instruction encoded through an LSTM, and then you have a recurrent policy either through a GRU or an LSTM that's predicting an action to take an action, turn left, turn right, go forward. Or you can have sort of cross-modal attention type methods where the instructions are being used to attend to spatial feature maps in RGB and depth channels, which are then ultimately used to feed into a policy. These are fairly representative of methods that are used in literature. And we also investigated the effect of the standard tricks and techniques that the VLN community has developed in terms of data augmentation, progress monitoring, imitation learning. The details are in the paper, and I won't go through this entire table. We have an exhaustive set of experiments, full, 2 to the 3 table of all possible tricks with all sorts of methods. The only thing I will ask you to focus on in this talk is look here, that 74-75% success is down to 32% already. When you actually have to navigate in continuous environments and you don't know where you are and you don't have access to the environment pre-explored, these methods are not that great. We were we had an inflated sense of success in a lot of these tasks. This is what 32% success looks like. This is a success case. So walk towards the railing, right past the stairs, walk into the living room and turn right, stop by the end table. This is the top-down map where the green is where the agent would have been navigating, and the blue line we'll see. Oops. The blue line we'll see is the continuous navigation. And so you can already tell that this is a much shorter navigation path on the nav graph than it is in the continuous space. Here's another example: walk down the hallway towards the window, past the kitchen, keep going, take a right, stop next to the rug on the couch. And so this is an agent that actually makes a mistake. It was supposed to keep going. It was then supposed to take a right and stop next to the rug in front of the couch. It actually does stop in front of a couch. I'll play this video again so you can see it. But it's not the right one. And so here's where the agent has ended up, and the red is where the agent was supposed to end up. Okay. Sorry, I'm just moving a couple of things around. Okay, and so those are the two things: vision and language from vision language navigation from image text pairs from the web, VLN in continuous environments. And finally, the third thing that I want to talk to you about is a slightly more challenging problem, which actually highlights exploration much more. So this is the task of room nav or room navigation. This was led by Medin Narasimhan, who's a PhD student at UC Berkeley with Trevor Darrow, and this work was done as part of her internship at Facebook AI Research, also in collaboration with Eric Wyvans, Shilne Chen, and the lead person here is Amanpreet Singh. The task here is room goal navigation. It is fairly related to vision and language navigation, but it is significantly harder. Here, the only thing you are told, you are spawned in an environment, and the only thing you are told is go to the nearest bedroom. That's it. There is no, there is no sequence of instructions given to you. You do not have the map. You only have RGB and depth perception. And so you have to understand where you are and explore. You have to find the room being mentioned as opposed to each step being told to you. And of course, the expectation is you will try to get as close as possible. Of course, it may not be possible, but as close as possible to following the shortest path to the destination. And again, the idea is that you'll adapt to unseen new environments. So in new environments, I can tell you to go to the nearest bedroom. This is an agent navigating, going down the hallway and stopping anywhere in the room. Okay. And I think our key observation is that houses have structure. Indoor environments in general have structure. And that structure can be understood in the relative arrangement of living rooms, bedrooms, bathrooms, kitchens, and dining rooms. That some spaces are small, some spaces are big, but there tends to be a particular structure to indoor environments. And so our key observation is that there is a pattern, there's regular structure in the data. It's based on architectural and stylistic patterns common to homes, human preferences, and cultural preferences. It's based, for example, dining rooms are close to kitchen, bedrooms are larger than bathrooms, and so on. And that an agent should learn them. We can train an agent to learn this structure, and it should use them. So it should hallucinate a belief map, a semantic belief map of room location before navigating to it. If you understand that you are currently in a kitchen, you have some belief about where other rooms in the house might be. You should learn this from real environments along the process of solving your task, and you should use it at test time. And so here's what a room location prior looks like. If you take a number of environments in the Matterport dataset and you align them so that the kitchens, the top-down maps, if you just rotate them and align them so that the kitchens are at the bottom left, you find that structure emerges. Bedrooms are roughly at the top right, living rooms are somewhere in the center, bathrooms are scattered a bit more over, and here are the dining rooms. So there is structure in the data, and our goal is to train a room navigation agent that will predict a top-down map and will navigate using the semantic map. So the maps we're going to construct are semantic maps. Here's an illustration. Here's an agent. Here's an egocentric view around the agent. We have rotated that so that we can sort of think of this as an allocentric view. And so this is where the kitchen is relative to the agent. This is where the dining room is relative to the agent. This is where the bedroom is relative to the agent. And already notice that the agent is looking forward, but it will be forced to make predictions everywhere. It will be forced to make predictions about areas it has not seen. These are amodal semantic maps, which means you predict even behind you and at places where you have never seen a pixel. You've never seen that area, but you will be forced to predict, where do you think the kitchen is? Where do you think the dining room is? And the color scheme, dark colors here indicate that that's where you think that room is. Lighter is not that room, and this is outside the house. There's a wall boundary. Here's a more realistic example. This is egocentric RGB. This is top-down map. Here's the agent navigating. This is the top-down map rotated so that the agent is at the center. Here's the goal. Here is a crop around that so that the agent is at the center, and it's predicting. The dark color here indicates that it's predicting the bathroom is behind it. This is ground truth. So this is what it will be asked to predict. The bathroom is behind it. The bedroom is where the agent is right now, and there is another bedroom ahead of it. There is no dining room in this crop around it, and so on. So these are the sort of semantic maps that we'll be predicting. And the way we will be using these maps is that the agent will use egocentric views and a recurrent policy to both predict the map. And once it has a map, it will predict a point it wants to navigate to on this 2D map, which will then be executed by a point goal navigation agent. And this is recurrent process. So it will at each point of time predict where it wants to go and try to move towards that. And I encourage you to check out the paper for more details. The way we're going to measure progress is, again, success and efficiency. And SPL is a metric that combines both of them. So if this is the agent start location, this is the closest point from the start in a particular distance threshold inside the room. So you have to at least enter 0.2 meters inside the room, and green is the shortest path. And if this is the agent path, we're going to compare, as long as you're inside this rectangle, you have succeeded, and the ratio of these paths will give you a sense of path efficiency. We've done a number of experiments. I won't go through all of them, but I will ask you to just look at this particular set of numbers. Our map generation plus point prediction plus point navigation gets to somewhere in the 30 to 35 SPL range, or 35 to 38 success range. It should be compared to, if you don't build a map, your success is around 15%. And if someone gave you the ground truth map and a point, if you just had to solve navigation, it's at 84%. And we also have ablations where if someone gave you the right map, but you had to predict the point yourself, it's better still. So this is the sort of landscape of things we're in. Better maps, better point predictions, things get better. But if you have to predict everything yourself, we're in the 30 to 35% range, which is interesting because now it seems like, compared to VLN, you can just give me the name of the room and that's sufficient. The agent can explore. We don't need full instructions, which is quite valuable. Here's a qualitative example of egocentric RGB, top-down map rotated for the agent being at the center. The agent is predicting a particular location. It's nearly perfect, that location. Sometimes it gets it wrong. That's what you saw here. Here are the maps being predicted. The dining room is behind it, kitchen is around it, and so on. And here's the ground truth map. Here's the resolution that it's being done at, and here's the generated map. Okay, so those are the three things that I wanted to talk to you about. VLN-BERT, VLN-CE, and room navigation. In all three cases, multimodal problems, combining vision, language, and action. And I think those modalities are sort of the interesting. I think as a community, these are where some of the interesting problems lie. I will, before I end, talk about a couple of quick teasers. So I want to mention that this year at CVPR, as I mentioned, we are organizing a workshop and a challenge. There's a challenge associated with it. And the challenge had two tracks. These were navigation challenges. The first track was point goal navigation, that given a particular random initialization of an agent in an environment, you're told go 5 meters north, 3 meters left relative to start. So this is a navigation challenge in which you're given point coordinates of where to go. And your input is RGB, depth, and just the goal vector, and you have to build an agent that produces a sequence of actions. And this is also a challenge that we had run in 2019. The new things this year is that we eliminated any localization sensors, following the same line of reasoning and argument that I made in the VLNCE paper, that indoor localization, assuming perfect localizers, is too strong an assumption. It's an unrealistic assumption. And so we removed it this year. We also did noisy actuation. So here is a top-down map with the black line showing what would happen if you follow a sequence of actions in the absence of any noisy actuation. So you would start here and you would end up here. And the red lines are different unrollings of the exact same sequence of actions, but in the presence of noisy actuation. And what you notice is that you can end up anywhere in the environment, because even though you're saying go forward, it actually doesn't have perfect actuation. So you can end up at different points in the environment following the exact same sequence of actuations, of actions. And finally, there were a number of cosmetic changes about camera positioning to match a real robot so that we could do sim to real experiments. The second task that challenge was held on was the object goal navigation. This is almost similar to the room navigation work that I mentioned, except you don't have to navigate to a room. You have to navigate to an object, but you don't know where it's located. So everything else is common. The input is RGB, depth. You know where you are, so localization was provided to you in this task. We did not want people to focus on localization for this task. We wanted them to focus on semantics, and you're told go find me a fireplace, and so you have to navigate in this house, find an instance of an object, and stop there. And this is for an example navigation where there's an agent. It's being told to, I think, find a table. There are multiple tables in the house. Each bounding box here indicates a particular instance of the table in the top-down map. The red pixels indicate in regions where if the agent stopped, it would be considered a successful place to stop because it is close enough. And so there are lots of places to be successful, but only one closest to you. And that's where that would give you the highest path efficiency. One thing I want to mention is that in these challenges, these are very different kind of challenges in that we ask people to write starter code, to write code that takes in observations and produces actions, containerize their code through Docker, which is a virtualization framework, and submit their code that can be run in new environments. So this is a different kind of challenge in that most challenges in the community, in the disembodied sort of learning community, are fairly based on sort of supervised learning. You submit your predictions, we evaluate it at test time, and you get a number back. This type of embodied environments require agents that can be deployed in new environments. And so we've built at Eval.ai infrastructure to handle this, that people can submit Dockerized versions of their code, which are run on a simulator in a cloud instance, and results appear on a leaderboard. So this is a fairly valuable infrastructure as we move towards embodied AI problems. Here are all the pointers to the things I mentioned. If you want to know about VLN-BERT, it's on arXiv. VLNCE is on arXiv as well. Our code is publicly available. And for any of the simulation efforts that I mentioned, this is the Habitat simulation platform, and information is available at this webpage. So I'll stop here. And the one sort of message that I'll leave people with is multimodality is important. I'm quite, this is something that I've been interested in for many years, and I'm quite thankful for the organizers to organize something on this topic. But I encourage everybody to think about transitioning from working in well-curated data sets that are available on the web to more embodied settings that are much closer to how humans learn, and B, to a number of applications that we need to get to. So with that, I'll stop and I can take questions. Thank you.
Thanks, Tarun. It's very interesting indeed. I mean, talking about embodied AI and embodied multimodal learning. So is this for questions? Do we have any questions from the audience? There's one from Macro. Can you talk yourself? Just unmute the mic.
I think we can read that. How hard is to transfer these navigation policies trained on simulation into the real world? Is it better to use depth maps or semantic segmentation as input?
Excellent question. Thank you, Marco. It depends what you mean by hard. First of all, there are two notions of hardness. One is, just the infrastructural challenges of you train something in simulation. Can you run it on a robot? Do you have to port your code base over to run it in ROS, which is what most robotics frameworks are dealt with. And then there's, of course, the more scientific question of do the sort of models that we train overfit in simulation? We have tackled both these questions in a paper that is out on arXiv called Sim to Real Predictivity. First, we have in that built-in engineering tools for, we've built a library called the Habitat PyRobot bridge. Habitat is a simulation platform. PyRobot is an effort out of Facebook AI Research Pittsburgh and CMU on standardizing, providing a Python-based library for deploying code on a couple of robots, the primary one being Locobot. It's a mobile navigation platform. And what we've done is we've built the engineering infrastructure so that simulation to reality transfer includes just one line change in a config. You say whether you want to run it in simulation or you want to run it on the real robot, and everything else in terms of PyTorch with your code base runs exactly the same. So you just have an if-else command. In terms of the scientific question, we have explicitly studied this. Train in simulation, then test in a new environment in simulation, and test in that same new environment in reality. So you have a lab scanned into simulation and that lab to conduct experiments in. And we've actually found that with careful setting of things, you can get fairly well-aligned results. So if results are working in simulation, they will also work in reality, which is not to say that we have solved the problem, that navigation in reality is a solved problem. All I'm saying is that there is a very nice one-to-one correspondence. When things work in simulation, they also appear to work well in reality. And the sorting of methods is the same from sim to real transfer, which means we can use simulation as a test time checking of methods. The second part of the question talks about depth maps or semantic segmentations. A quick answer there, because I know there are other questions also being asked. The quick answer there is for navigation, we found depth maps to work really well, point goal navigation. But I think it's mostly because the goal is specified with a coordinate. There are no semantic understanding required. For object goal navigation, we do find that RGB is better than depth, and using semantic segmentations is better than RGB. So yes, I think intermediate representations, which are more semantic, is quite valuable.
Okay, so there's another question from Iran Lee, that what is the limitation of current embodied environment? So what it takes to create one that will transform embodied AI like ImageNet or Common Cloud Dataset for NLP?
That's an excellent question. This talk was not about Habitat or all the other efforts, but I have a talk online on Habitat, and I encourage you to look at it. Creating the ImageNet COCO VQA of embodied AI is exactly our scientific mission for Habitat. That's what we've set out to do. And it's a multi-institution, multi-year effort, and I'm fairly confident in the progress that we're making. What are the limitations? I think there are a number of limitations. And I can try to decompose them into data, simulator, and tasks. So at the data level, ImageNet was only possible because a decade before that, a number of other efforts happened, and there was sort of like an internet and smartphone revolution. Everybody was roaming around with cameras that they could take pictures on. Uploading it to the cloud was cheap, and there were reasons why people wanted to do that. You wanted to share pictures with your friends and family. That allowed massive creations of data sets to be formed. We are not there with 3D data sets yet. It's coming. Our smartphones now have stereo cameras, there are depth sensors, but when there is reason for people to create 3D scans of their environments, upload it, and send links to each other for something, that's when we will see the 3D data sets bloom. When the flicker of 3D data sets happens, that's when a lot of these downstream research tasks will become easy. So right now we're highly data starved in this region. The limitations in terms of simulators are that we have to simulate not only image generation, so rendering, but there's also physical simulation. There was a very nice panel on simulators at the Embodied AI workshop, which is recorded. I encourage you to check that out. There's a much deeper discussion there than I could possibly get into here. And I think finally at the task level, in ImageNet and image detection, we kind of understood that if you can solve image classification and detection, if that performance goes up, everything downstream also benefits. It is not clear right now what the image classification version of embodied AI is. Is it point goal navigation? I don't know. There's no semantics in it. So that particular definition of a task will take a while to emerge.
Okay. Actually, I have another question.
Dhruv,
I
have a question.
Oh, yeah. Please go ahead.
I have a question. Giovanni.
So,
hi, Dhruv.
Sure,
Thank
Giovanni.
You for amazing talk. I was thinking if you are thinking to include humans in habitats, because that could be very interesting to do human goal navigation, for instance, when a robot should interact with a human. The work you have done is super amazing, and all my students, also Marco, is attending and working with habitats and reading papers. But one point we want to work with are humans as well. Do you think there would be chance to have in the future possibility to include humans on habitats?
Yeah. Thank you for the question, Giovanni. And it's always nice to hear people are using it. This was for us more than just a paper. We will continue to maintain this code base. This is a multi-year effort, so you should feel confident that it's always nice to hear that there are people using it. So that's great. Humans in habitat, there are actually two ways of doing this. There are two versions of this question. One is asking, can I have human avatars? Can I render human 3D meshes in simulation? And can they move around so that maybe a robot can follow them? Can you study person detection problems in simulation from various viewpoints and so on? That's one version of the question. The other version of the question is, can we bring actual people into simulation? Can we do data collection from humans in a simulated environment? Can we ask them questions? Can they bring in language? Can they show action demonstrations and things? We are interested in both. There are technical challenges involved in both. In the first one, getting human meshes in, my understanding is that this is right now, the way it's done is it's largely done the way video games handle it, that you create some animation avatars and then you pre-render any movement, like they're going to move in a certain way, and then you render that out in simulation. Simulating contact between human bodies and pushing them in simulation is a hard problem, and also photorealistic rendering of human meshes is difficult in simulation. Having said that, we do have some efforts in that direction. So Manolis Sava and Hanbyul Ju at Facebook AI Research, they're both studying this problem. And I would say it's still in the realm of research, but we hope to report something on that in, I would say, 6 to 10 months. On the second direction of human data collection, I think that one is much more manageable. It requires running Habitat in a browser, which we have already built that capability, so we can connect it to Amazon Mechanical Turk, so that humans can almost treat this, drive this robot in simulation. You can have data collection by asking humans questions. That is much more manageable, and I think we can get there.
Okay, thanks.
Thank you very much.
Thanks. Due to time, we have to stop. Unfortunately. I want to thank you again. It's a very inspiring talk. I hope others can contact you if they have some questions. Yeah,
absolutely.
Thank
you. Thank you, Michael, and thank you, Mir, and the rest of organizers.
Thanks.
Okay, we will shift to the next one.
Yes, so we're going to continue with the orals. The first talk is titled Exploring Phrase Grounding Without Training, Contextualization and Extension to